continue to talk about the hash used in multimedia, especially to analyze the multimedia content and to do the application like the retrieval or to find the similar sets. Okay, now the topic would be we use the hash function to generate the binary codes, or we call it to do the binary embedding. Okay, so in binary embedding, if we want to use the hash functions, okay, so generally we will partition the data set. For each data, we will use a hash function to divide the data space into two parts, and belong to one part we can give all data in one space. Subspace is bit 1, and another space give us bit 0. But the general idea to use hash function, and each hash function can generate 1 bit to encode the data. Okay, so it's a general hash function is expressed like this. Okay, so you can see give your data point x, and the hash function, the k hash function can be expressed generally like this. Okay, so the x is a vector, so you can we use the w. You can think it's weight. Okay, so use over in the space. You can think it's just a hyperplane. The hyperplane parameters. Okay, so the w ties with x, and the plus is bios, and then you can use another function. It's usually use a linear function. It's okay. And finally, remember to use a sign function. The sign function is according to your value. If it's positive, we can encode it as bit 1. Otherwise, we encode it as 0. But in some papers, they will express the bit 0 as -1. But it's because in some mathematics expression, it's easy to formulate -1 rather than 0. OK， 我的意思是说，就我们会用最后这个 sign 方式嘛，根据它里面的数据是正的还是负的，来给它是 bit 1或者是0。那不过在有一些论文里面呢，它会用-1来代表0，那是因为它的数学表示法里面，它用-1来表示会比较容易去做计算。那但是其实-1最后会把它变成 bit 0，是一样的意思。OK。Okay, so last week we already mentioned about this. So how to use your hash function? You will use a set of hash functions. You can generate a set of binary bits. Okay, so for example, here I use 4 hash functions from h1 to h4. You can see in the 2D space they generally can be represented as a straight line. Okay, so each line partition the space into 2 subspaces. So you can, according to this, belong to which subspace, give the code as 0 or 1. So here we use 4 hash functions, so we can generate 4 bits for each data point, and we can use the hash code to generate an inverted file system like this. Okay, so for example, this means if your binary code is 0110, okay, so we can store your data point in this bucket, like x1 and the xn. This data points, the binary code is 0110. Okay, so you build such an inverted index, and it helps you easy to access the data. Okay, so it's what we call build index structure based on your binary codes. Okay. And then to do the search, okay, so you can use this way to easily find your possible candidates, your nearest neighbors. If you query Q, we will apply the same hash function to generate this hash code, and we can use this hash code to find my candidate by using where the codes. For example, I hope my codes, the clusters should be their Hamming distance range is smaller than 1. Okay, so all these codes, their Hamming distance to the query is smaller than 1. Small or equal to 1. Okay, so you can list a set of candidate codes and just to search their inverted files and to find their candidates stored in this bucket. Okay, any problems? So in general, such a hash-based representation and the index structure is very efficient because the computation between the Hamming codes, between the Hamming distance, you can just use XO and use the publication count. Publication count is to count in your binary code how many bit 1 appears, its frequency. So all XO and the publication count are already implemented as hardware instructions, so they can perform very efficiently. So that's why use the Hamming to generate, use the hash to generate the binary code can be very, very efficient. And also it has advantage on its space consumption. It's very compact. Okay, you can see if the original data set like 1 billion dict description is 96 dimensional real valued vector. So if you want to store all the data, you need to prepare more than 700 gigabytes. Okay, but if we do the hashing, compress the vector into a hash code. For example, we use 256 bits to encode each vector. Okay, so generally, to store all the 1 billion 256 bits vectors, you just need 32 gigabytes. So you compress a lot, and so that you can save a lot of memory space. Okay, it's generally recall for the last week. Okay, any problems? Okay, so next we will introduce the LSH family first. So first is LSH family, and later we will introduce the learning-based hash function. Okay, so LSH-based family basically it doesn't use any label information, so you can regard it as unsupervised learning. Okay, so in LSH we will generate a set of hash functions, and this hash functions has the following characteristics. Okay. The probability of 2 points that having the same bits is proportional to their similarity. So it's similar to our last week's topic. So we talk about we hope to generate the same code. What's the probability they have the same hash value? Here, what's the probability we have the same hash bit? So the same idea. Okay? Same idea to last week we mentioned. Okay, we can generally express like this. Okay, so the probability of the hash function of xi equal to the hash of xj. The probability to be equal is equal. This can be expressed by the similarity between xi and xj. Okay, so there are 2 general categories belong to the LSH family. One is the random projection hashing. It's usually used for vector representation of the database. And the second is a random permutation hashing. Okay, you usually use it for the state representation. So if your data set is a set of tokens, okay, you can choose this one. If your data set is a set of vectors, you can choose the random projection hashing. Okay, so first is a random projection hashing. Okay, it's a function. It's typically expressed like this. Okay, so you see it's very similar to the general hash function, right? So we have your weight and time is x and plus is your files. And according to their value, we use the sign function to determine this bit is 1 or 0. Okay, if it's positive, we assign it as 1. Otherwise, it's 0. Okay, so if we want to use random projection hashing, let us the first, how to generate your random vector W and B. They have to follow. The random vector W is generated from a standard Gaussian distribution. Okay, so it's a very common assumption. Also, okay, so just use the Gaussian distribution to generate your weight, and then the correlation of the probability between any two data points xi and xj is determined by their angle theta. Okay, here is the example. You see the xi and the xj and their angle between them is denoted as theta ij. Okay, so if they are very close, the theta ij will be small, right? And their inner product will be large. Okay, it's a general characteristic between the xi and xj. So the probability of the two vectors xi and xj. So according to the h function, they will have the same bit. The probability is equal to the 1 minus to the theta ij, their angle, and divided by pi. Okay. Okay, so it's a general idea of random projection hashing. Okay, the conclusion is how to generate the random projection is easy, and the theory, I just skip the theory analysis here, but the conclusion is very easy. Okay, but generally, if you want to obtain a high precision means I hope what the data I retrieved is exactly the same as my answer. Okay, so I hope the precision should be high. If you want a high precision, you should generate a long hash code. Okay, so it means you should use more hash functions to generate your hash codes. Okay, but if you use a long hash codes, it usually harm your recall. Your recall rate will be degraded. Okay, because precision and the recall rate are usually trade-off. Okay, so that's the idea. The idea is we can use multiple hash tables and try to use this to balance the precision and recall. Okay, so it means we can given n hash tables, and each hash tables contain k bits. So we can calculate the correlation probability at least one table is close to this. So this is mean in each table it contains k bits. So if the k bits are all the same, the probability is like this, right? It's a similarity between xi and xj. And if all the k bits are the same, the probability is like this. But the probability will be very small if K use a large K, right? So you can kind with use any tables. Each table, the probability is like this. But if it's very small, you want to increase your recall, you can perform it to n tables, so that your collision rate, your hit rate will be increased. As this. Okay, it's just the set as we show you last week. Let me show you. Remember the analysis here? We want to find a similar set. Here we show, if we hold the two documents, they are identical, at least one of the 20 base. Okay, we can calculate like this. So here, the 20 base is equal to the index table, the number of tables you want. Okay, so the same calculation here. Okay, so exactly the same. Okay, so this make you just to adjust how many index table and how many bits in each index table. Just adjust n and k to try to achieve a balance between precision and recall. Okay, any problems? Yes. 派就是那个，派就是算那个角度的那个派，就是纯粹就是我们要有个 normalization。theta 是一个角度，是 the angle between the two, the xi and xz, the two vectors. Okay, so theta is the angle and the pi is just the, okay, think it's like a normalization to represent is the radius. So any problems? Okay, theta. This is a theta between Si and Xz. Okay, so we will use pi as a denominator here. Okay, so next is a random permutation H. Okay, a typical H function is the mean H. Okay, so mean H we already mentioned in next week. Okay, so it's expressed like this. The probability between two data points, okay, is proportional to the Jacob. It's actually exact to the Jacob coefficient like this. The intersection between two sets divided by the union between the two sets. Okay, so it's mean H. Okay, so because mean H is used the computation to generate to perform the process. So that's why we call it a random computation. Okay, just to recall last week the topic about the mean H. Okay, so here is a different H function is called sin H. So it's 20 years ago. Okay, but it's a very representative, very famous H functions to generate a very compact binary code. I use these the examples to illustrate the idea. Okay, give you a document. Okay, the document you can extract many tokens from it. Okay, so you suppose you extract n tokens, and each tokens you represent as a feature vector here, and each token you have corresponding weights. W1 to Wn. And then, according to the vector representation, we transform it, use a hash function to transform it into a binary code. You see here are 6-bit binary code. Okay, so for each token, we generate the binary code by using a hash function. And then, next step, we will, according to the weight and the binary code, to generate a weighted binary representation. Okay, like this. If the code, the bit is 1, we generate W1. If the bit is 0, we generate negative W1. Okay, we just follow this step. Okay, so for 1, 0, 0, 1, 1, 0 is we can produce a W1 and the negative, and the negative, W1, W1, and the negative W1. Okay, we just follow the same process. Okay, for all the n binary codes, and all of these, you see, each one is a 6-dimensional values vector, and we have n such vectors. We just sum of them together. The sum of them to generate. Okay, so here, suppose the summation is like this. You see, it's 13 and 108 and so on. Then we apply the sine function to see if it's positive, we generate the bit 1. If the second component is positive, okay, we generate bit 1. But for the third, it's negative 22. So we generate bit 0. So similar idea, we use the sine function to generate, we call here is a fingerprint. Then this fingerprint is used to express this document. Okay, so it's an easy idea to compress or to quantize a document by following this step to generate a very compact binary code as a fingerprint.
Okay, any problems?
Okay, the sync hash and the main hash, before they are deployed by Google. Okay, the Google used this to try to, there are billions, more than billions web pages on web. So if you want to do image detection or web page detections, they can use this way to generate hash codes and to do the computation. Okay, also like in Google News, they can use to find the similar news and to group them together. Okay, so these two methods already employed by Google, and there is a paper to compare the two methods. Okay, if you are interested about these two simple methods, you can refer to this paper to see a comparison. Okay, so then we go to the next subtopic. We talk about the learning-based hashing. Okay, learning-based hashing means we have to consider the data dependence. Okay, before, if we use the random projection or random computation, we don't consider the data distribution. But so it's belong to the data independence. Yeah, but if you consider the data dependence, okay, you want to learn a more meaningful distribution or more meaningful information from it. Okay, so we can consider use machine learning to learn from your training data set. Okay, generally there are three categories. First is unsupervised. So we use unlabeled data to do the learning. Okay, the unlabeled data we can use the data distributions or the manifold structure. The manifold structure means we try to use the neighbor informations, okay, to learn it. And the second category is supervised. Okay, here we use the label data. Use the label to do the supervision. The last is semi-supervised. We will use both labeled and unlabeled data. Okay. The first method I introduced here is iterative quantization. It's called ITQ. ITQ is published in CVPI 2011. Okay, so it's belong to unsupervised learning-based application, and it's the MATLAB code. The syntax of MATLAB is very close to Python. Okay, so you can easily to translate it into a Python code. Okay, you see, it's very compact. Just a dozen of lines. You can finish ITQ. Alright, so later I will illustrate this background theory. And first, we see a paper, and here he gives an example. There are three figures. Okay, the first figure is suppose we have data distribution like this. It seems like the data distribution contains two groups, and each group is like a Gaussian distribution. Okay, so if you perform, suppose your data set is like this, project to the 2D on a 2D space, the distribution is like this. Okay, then you perform the PCA. PCA is the principal component analysis. If you perform the PCA, you can find two principal components, or mean the eigenvectors. This is the first eigenvector here, the second eigenvector. The first eigenvector means the data distribution, the data project to the first eigenvector, they will generate the largest variance between them. So that's why we call it eigenvector. Okay, eigenvector will have the first eigenvector will have the largest eigenvalue. The largest the eigenvalue means is the variance. Okay, the largest variance will be P as your first eigenvector here. Okay, and then this is the second eigenvector, and then each eigenvector should be perpendicular. Okay. Okay, so like this, and then based on this, we want to do binary code to do the quantization. Okay, so you can see there are 4 regions, right? And then here you treat this in the center. It's the orange. The coordinates is 0, 0. And there are 4 corners. This corner belongs to 1, 1. The coordinates to 1, 1 is -1 and 1. It's -1, -1. And this corner is 1 and then -1. Okay. Then, so you just treat each corner is your hash bits. You have 2 bits to encode this data. Okay, so for the data point, it belongs to the first region. You will encode it as 1, 1. Your binary code is 1, 1. And the quantization error will be the distance from the coordinates here to the data point. This distance is we call the quantization error. Okay. Okay, so for all the data here belong to the first region, they will encode it as 1, 1. And for the second region, here we will encode it as -1 and 1. Okay, remember here we use the -1 as a bit. We will encode it as bit 0. Okay, negative we will encode it as 0. But in mathematical expression, they use the -1. It's easier to express their concept. Okay, so it's -1 and 1, but in binary code it will be 0, 1, 2 bits. Okay, and here for this region, they will all encode it as -1, -1, and this region encoded as 1 and -1. And we just use this assignment to calculate the average quantization error. Here in figure A, the error will be 1. Okay, any problems? It's a simple way. Just if we don't do any processing, we just simply assign all this data according to your item space and to assign them to their nearest corners. Okay, it's a very easy way to do the hashing. But the quantization error, I have to say, is high. Okay, then in figure B, we perform a random rotation on this data. So what's it mean? This means that we just center as the origin and then to rotate your data like this. So you see data before is the distribution is like this, but after we rotate around your origin, you see it's like we rotate 30 degrees. Okay, so what happened? Now we follow the same idea to assign all this data to 1, 1, and here to -1, 1. Okay, we just follow the same way, but only the difference is the data is rotating, and we calculate the quantization error again. It's reduced to 0.93. Before it's 1, now it's reduced 0.93. So just do a simple rotation, you can achieve a better quantization. Okay, got it? Yes.
就是做完 PCA 的时候再做。
如果说你只做 PC， 应该说对，它这个目的是先做 PC 的没错。好，但是如果你只做 PCA 的话，它的分布就会像这样，就会像这一图的，那就是纯粹是根据你的那个 variance 最大的来去做那个对应。好，你就会发现说，这样子的quantization error是比较大的，因为它的分布很特别，它是2个这样很特别的一种分布，它故意设计成这样。好，那这种分布下你的那个 error 就是比较大。对，所以先做 PCA 做完之后，我们再做 ABC 这些处理。Okay, so any other problem? So just do a simple rotation, a random rotation, you can reduce the quantization error. And the figure C shows the optimal rotation, like this. So if all the data we rotate about 45 degrees. Okay, so you can see all the data, most of the data, they will encode it as 1, 1. And for this data, we will encode it as -1 and -1. And then you compute the quantization error. It's further reduced to 0.88. So the ITQ is trying to find the best rotation angle and do the best based on the rotation angle, and to do your hash assignment, you can reduce your quantization error.
So any problems? Okay.
So real is real. Just do a rotation and reduce the quadrature error. Yeah, but I think these figures give you a good example. Yeah, so for such a data distributions, so although it's an artifact, the human generated data distribution like this, but I think it's give a very good illustration why the rotation can help you to reduce the quantization error.
那你们觉得很奇怪吗？
很神奇吗？rotation 就可以减少有变化误差。
像你讲到类似，
对，其实这个类似的概念在线性代数里面常常用到，所以见怪不怪。所以做其实你就不会觉得很奇怪。我说，这真的有用。有上学期我们有讲过这个类似的，在讲 product quantization， 我们在讲 optimize product quantization. Do you remember? Product quantization, we just rotate your data, then you can achieve a better quantization. You can reduce your quantization error. Yeah, the same idea. Okay, any problems? Okay, so these figures I just show you four different ways to do the quantization. Okay, first is LSH. Okay, so you see this data point distribution like this. All these subfigures they have the data. All the data distribution are the same. Okay, for LSH here, here we generate two random vectors. Okay, so first one and the second one. Okay, generally it's divided. It divides the space into four regions. Okay, and these four regions, for data points belong to the upper region, they are encoded as 1, 1. And for data belong to this region, will encoded as 0, 1. But here is no data belong to this region. And the data point belong to here is encoded as 0, 0. And here is encoded as 1, 0. Okay, it's an idea of realization. Any problems? Okay, the two vectors, the two random projection vectors are randomly generated. Okay, so you can see the space. They look not very, they are not equal. The region space looks not equal. Okay, so next, for this figure is a k-means result. Okay, k-means here we also try to generate 4 centroids. This means we want to produce 4 clusters. And each clusters, okay, so after we perform the k-means, in general, the centroid will be located in the middle of this data in the group. Okay, so you see this is the result of k-means, and the cross point means the centroid. You see the centroid is just, I think it's well described the data distribution about this data set. Okay. In general, the k-means can produce the minimum quantization error. Because you see, in each group, all the data to the centroids, the quantization error from the point to the centroid is a quantization error. It's very small compared with others. Okay, so k-means is usually can perform you can get the minimum quantization error. Okay. check the ITQ. Okay, so ITQ, so it's before we do the rotation here, we will divide the data into according to the two eigenvectors and assign the hash codes, okay, according to probability that belong. Okay, so you can see from this figure, the convention error to the binary code is very large. Right? For example, here, the code is 00, and the correlation error for this point to 00 here is very large. Okay, for each data point, they have a very large correlation error. But after we do the rotation, you can see in this figure, we apply the ITQ after the rotation, find the optimal rotation angle. So here we don't rotate. Here we don't rotate your data. We just rotate your eigenvectors. The same. The idea is the same. Just rotate. Okay, so you can see we rotate 45 degrees, and then you can see. Based on this, we can generate. You see the coordinates for 1, the correlation error between all these data points is much smaller. Yeah, you can see very clear compared to this one. Compared to all the regions, you can see you can produce a smaller correlation error. Okay, any problems? Okay, so this figure I borrowed from another paper, and here we'll just show you that the distribution and compare with their MAT, the mean average precision. And if you have a lower distortion, a lower convention error, you usually get a higher MAP. Okay, so it's intuitive. So you see, if we use here, we show with all the method, we just encode all the data point to 16 bits. All these methods. We just compress the original data point to 16 bits. And you can see means get a highest MAP because its distribution is lowest. Okay, it's another data set called GIST, and this is the data set in C. Okay, so in all the two data sets, K-means get the highest MAP because its distortion is the lowest. And then is the PQ2. PQ2 means I divide the vector into two segments. Okay, remember in last semester we talked about PQ, right? And the PQ4 we divide it into 4 segments, PQ8 a segment, and the ITQ unfortunately has the highest distortion here, so its MAP is lowest. Okay, so it's a comparison between PQ, ITQ, and the K-means. But since ITQ, although ITQ get the lowest MAP, but its value is very compact. Its computation can be very fast. Even all of them are 16-bit encoding, but use ITQ is a binary code. The computation is very efficient. Okay, and all the others, PQ or K-means, they are still the real value back. Okay, so if you compute with the real value back, but ITQ compute as a binary code, it's extremely fast. much faster than the other method. So it's a trade-off. You want to choose between the accuracy and the efficiency. Okay, any problems? 好，你基本上 ITQ 它虽然很不准嘛，因为它把资料都压成 binary code， 它本来就损失资讯损失非常的惨重，所以它很不准。但是它速度非常快，是它的优点。所以一定是这样子，你就是要在速度跟准确度里面做取舍。Okay. Okay. Next, we go dive into how to do the ITQ. Here is the algorithm. Okay, so here the input is we have a zero center data points. X1 to Xn. Okay, they are in a D-dimensional space. And the output, based on this training data, is our input training data, and the output will be your weight matrix W, and the rotation matrix R, and a binary code for each data point B. Okay, so you have n data points, and each data point will be compressed to a C-bit binary code. The binary code is in the range -1, and the binary code will be -1 and 1. And remember, -1 means bit 0. Okay. Okay, so we have to generate 2 steps. The first step, we perform the dimensionality reduction by PCA. Okay, it's a very common used technique to reduce your dimension. Okay, so you can use it, and then you generate. You can find the eigenvectors. We choose the top C eigenvectors. So it depends on how many bits you want to generate. Okay, here we want to generate C bits for each data point. So we have to keep top C eigenvectors here. And so that we can project every data point to the weight matrix, to the weight matrix, so that we generate a C-dimensional data point. Okay, so now from your original data is X, but X is D-dimensional. But after the projection by PCA, now we get a new vector B. B's dimension is C dimensions. Okay, we use this to reduce your dimensionality. It's a very common technique to do dimensionality reduction. 好，by using PCA. 好，这是一个很常见的降维的做法。用 PCA 来做，只要找到它的 PCA 的前7个维度，最大就是最大的那个eigenvalue 最大的那个 eigenvector， 好，那就可以直接做投影降维，从原来的维度来是低维，维度是低嘛，这样降就降到C维，维度变C，好，然后接下来每个维度我们再做 hash， 好，就做 hash function， 把它降到。变成binary code， 7个 bit binary code. So for the first step, any problems? Okay. Then the second step, we try to minimize the quantization loss. Is formulated like this: the loss function. I give you the binary code and the rotation. I hope the binary code and the distance to the reduced vector and the time with the rotation. VR means the reduced vector by PCA, and then we rotate your data so that this quantization to the binary code is minimized. This part we call the quantization value, right? We want to minimize. this loss function. And to minimize the loss function, you have to update B, the binary code, and R, the rotation matrix. You have to update the two parameters. Okay, then here they apply an EN algorithm to update the parameters. Okay, so to minimize the above quantization loss, okay, so we can perform like two-step to optimize, because we have two parameters to do the optimization. So the general idea is like the K-means cluster, like the EN algorithm, exploitation maximization algorithm. Okay, so two steps. First, we fix the rotation matrix to update your binary code matrix. And the second step is to fix your binary code and update your rotation. And we just repeat these two steps several iterations. So that's why we call it an iteration. Okay, the main is ITQ, iterative quantization, because its algorithms performs the learning iterative. Okay, so how to do the first step? Fix your rotation matrix and to update your B. How to do it? Okay, the idea is at the beginning we first randomly generate the rotation matrix R. It's random generate R. And then we fix R to update B. So it means we will try to assign all the data points according to this data to assign to the nearest corner. Okay, so here is a expression, the mathematical expression. The Q, our loss function is here, right? We just expanded it. We can get the B squared plus VR, V times R squared, and minus the 2 by this TR means trace. Trace is a diagonal. The sum of the diagonal elements. Okay, the trace of the BR. Okay, so the expansion of the B minus BR squared is like this. Okay, so here B squared is equal to this. The number of data and the number of your dimensions is always fixed. And the VRF, we don't care, because we fix R, so we cannot update R here. So we just skip it. And also NC is fixed, so we skip it. The only key component is this B. We want to update B according to this equation. Okay. Okay, if we want, so this is the only component we can do the optimization. Okay, what it is, we want to minimize the negative 2 trace of this. This means we want to maximize this. Right? To minimize the negative 1, this means to maximize this. Right? Okay, so the trace of the BRB can be expressed like this. The B is actually the R times B, RB. We just express as a B cubed. And the length, this means the B is located, R is the range. You mean before V is original, the dimension reduced vector, and after we rotate it, then we just check if it's greater than 0, we assign its bit as 1. If it's more than 0, then we assign it as -1. Then with this policy, we can get the maximized value of this term. Got it? So if it's positive, the bit should be 1. If it's negative, the bit should be -1. So that it's always, their product is always positive. So that this term will be maximum. 好，这个观念就是说，你知道，如果说你是正数，这个是旋转后的那个值，旋转后的那个下面的值。好，如果它是正数的话，你这个就要是1嘛。如果这是负数的话，你就要负1嘛。这样的话，这个地方的成绩永远是正数，这个就会得到一个最大的值。我要去 maximize， 就这样做而已，就是 maximize。就做这样的筛就可以得到最大的这个特点。Okay, so it's the idea we have illustrated in the previous figure. You can just build a connection between the previous illustration. Okay, so it's no problem. Okay, the second step, we update R and fix your binary code and to update your rotation matrix. And the next problem, if in this expression you want to B is fixed and the B is fixed and R, you want to update R. Actually, there is analytic form. You just compute the SVD, singular value decomposition of the B, DE, and find S, and then you can get R is equal to the S times S. There is an analytic solution. 还有唯一的解析解，就直接线性代数就可以算出来，解这个式子，就是 B 跟 B 都固定了，只有 R 要改变，要让它最小，所以我们直接的线性代数解就可以解出来。Okay, so let's spot. Then you can find the base R under this situation. Then go back again to fix R to update the B until you just repeat this iteration several times and until they are converged. It means that R and B is no more chain. Then you can start the iterative optimization. Any problems? Okay, so it's a very classic method and a very efficient, very effective way to generate binary code without any label information. It's unsupervised and can perform very effective. And the result, I think its performance is also comparable with even, okay, so later we will use the deep learning hash. So it's a current trend. Okay, apply deep learning to do hash so that they can learn a better relation between the data distribution. Okay, but the ITQ just give you a very elegant and very efficient way to do hash. Okay, let's take a break and we will continue.